In example 2, suppose that in the simple circuit of figure 9, the resistance is 12 ohms, the inductance is 4 henries, and a battery gives a constant voltage of 60 volts. We want to be able to draw a direction field for equation 1 with these values. So equation 1 is taking L multiplied by the derivative of I with respect to t plus R times I equals E of t. So we're going to let L equal 4 since that is the inductance. We know that R is the resistant, which is 12 ohms, and then E of t is the amount of voltage. So here is our equation, and then subtracting 12I to both sides and dividing it by 4 gives us the following. And so the direction field for this differential equation is now shown in figure 10. Now, what can you say about the limiting value of the current? Well, as you can see here, that the line segments are kind of going towards a line here, and you can see here that that line is at 5, which is a horizontal line. And every segment is the same, and that looks like it's got a slope of 0. So that means anything underneath here is actually hitting that horizontal line at 5. Likewise, on the other side, or on top of that, it's also approaching the Y value at 5. So what can you say about the limiting value of the current? Well, it appears that from the direction field that all solutions approach the value at 5a, and that is the limit as t approaches infinity, the current of that function of t is going to equal 5. And so in part C, we want to identify any equilibrium solutions. So it appears that the constant function I of t is equal to 5, because that's where the limit, it's an equilibrium solution. So what we're going to do is, in the differential equation, 15 minus 3i, we're going to let I equal 5. So if we know the left side of dl dt is equal to 0, then the right side is 15 minus 3 times 5, which is also equal to 0. In part D, if the switch is closed when t is equal to 0, so the current starts with I of 0 equals 0, use the direction field to sketch the solution curve. So if we know that the input is 0 and the output is 0, that means the ordered pair is 0, 0, which means that the direction field should pass through the point 0, 0. So if you're starting at 0, 0, knowing that it passes through, well, the direction field gives you a curve, and if you watch the segments, it actually starts turning towards the limit of when that function is 5, where that function is 5. So therefore, this one in red is the graph when t is equal to 0. Now, if you notice from figure 10 that the line segments along any horizontal line are parallel, that is because the independent variable t does not occur on the right side of the equation, I prime is equal to 15 minus 3i. So in general, a differential equation of the form y prime is equal to f of y, in which the independent variable is missing from the right side, is called autonomous. For such an equation, the slopes corresponding to two different points with the same y coordinate must be equal. This means that if we know one solution to an autonomous differential equation, then we can obtain infinitely many others just by shifting the graph of the known solution to the right or left. In figure 11, we have shown the solutions that resulting from shifting the solution curve of example 2, 1 and 2 time units, namely seconds, to the right. They correspond to closing the switch when t is equal to 1 and when t is equal to 2.